Hello. I've been doing data science since the mid 90s. You realize that's about a decade before the term got coined, but that's kind of the point here. The data science has been called a lot of different things over the years. Data science, data mining, machine learning. The names change, the principles don't. How you do data science has stayed pretty well the same for a lot of years. And that's what I want to talk about here, how to do data science. Now, today I want to talk about there's a particular technique I've seen a lot over the years. It's very persistent and it's a bad idea. It's called target encoding. It's actually a anti-pattern in data science. It's something that looks good, sounds good, but will actually give you terrible results in the long term. Now, what it is, start off with a categorical variable that has a whole lot of classes. Zip code is the canonical example here. For each class, then you calculate the target value, the average target value in that class. Now, make this a new numeric variable in your model and replace the original categorical variable with this numeric variable. Typically, it'll make your reported results look great, but this is a mirage. Now, why this is a bad idea? First off, this is a very complicated way of putting the target variable in with your prediction variables. This is bad data science 101. Don't mix the target in with your prediction. Second, there's a stability issue. Remember that a model only has value on data that doesn't exist yet. We report on what we can, but the real value of models is in the future in their deployment on data that doesn't exist. Now, if I want to do that deployment, I've got to make the claim that the patterns I'm seeing now are going to hold in the future. If I can't understand the patterns I'm seeing now, if I've got, well, zip code has this effect that we don't understand, but we're using it, I can't make the promise that it's going to be stable. Now, even if I'm going to be more than modeling noise, even if there's a real signal, a real zip code level effect there, then I don't know if it's temporary or not. For instance, let's say I've got a competitor in Texas that is having a big sale at the time I'm doing my analysis. I'm going to see very high attrition. Well, if I deploy and the competitor stops having that sale, my model is going to misunderstand Texas and also any place there is a sale. Now, when it comes to evaluating data science techniques, I've got a principle that if I can get signal from random data, I'm doing something very bad. Now, I've got a worked example for this. I'm going to switch over to Jupyter Lab. So start off by importing everything in sight. Make the letters, Cartesian product, 24 cases. There's got to be a more Pythonic way of doing it, but oh well. Make a target variable. Here's what our data looks like. I've got what I think is going to be a predictive variable, a target 0, 1. Now, make the encoding, rename the encoding. So now I've got an encoding data field that looks like this. So in class AAA, I've got a 71% positive rate. In class AAD, I've got a 29% positive rate. Let's make a histogram. Histogram looks pretty interesting. Now, looking at the histogram and looking at the encoding, our first thought is, hey, there's something really interesting here. But remember, we know this is all random. Anything interesting we see is a mirage. Now, training and test data. Um, Now do a logistic regression, keeping things simple. So I'm not doing deep learning, just logistic regression. Calculate stuff. I want to test the model now. I want to make a confusion matrix, a chi-squared, and calculate the AU statistic of the ROC curve. So the confusion matrix looks good. Chi-squared, it's amazingly significant. The ROC, if I'm having random noise, a random score, I'll have a ROC AUC of 0.5. This is 0.62, which is decent. I mean, it's not something to write home about. It's not something to cheer about, but it's real. And it's also going back to the training data set. The training has a slightly lower AUC score. Now, so what that means is in the data set, there's very little memorization. This is great. I mean, this thing is passing all of our classic data science tests, except we know we're getting a model on random noise. There's a technique I've heard of about smoothing that is supposed to help a lot. Let's see what it does. The technique is it's a kind of semi-Bayesian idea. You take the class score, the target score in each class, and the overall average. You make a weighted average between the two with the number of cases in each class on the one side and something you pick out of thin air on the other. Here I'm using a weight of 8. So I'm making a smoothing that'll get things closer to average, do all the things, get a new confusion data set, still looking great. The numbers are different. We've changed the data, but the problem has not gone away. The ROC is still good. Test is still better than train for some reason. They're pretty good. I'd have to say classically that there's no memorization here. But again, we're getting a model out of originally random noise. And that's the big problem with the target encoding procedure. You're modeling noise. So now I want to talk about, we've just realized that we should not do target encoding. What can we do? Well, first off, and I'll only be a little facetious here, good luck. I mean, dealing with high category variables is very difficult. It seems like there's a whole lot there, but they're a mess. The best thing, I think, is to try replacing what you've got with some kind of meaningful, fair, stable, continuous feature, like average income per zip code. How do you figure out what's good? Well, do data analysis. What will happen? There's something, if we make the encoding on the trained data only, well, what'll happen is the test results will be terrible, i.e. noise, which is good. If I'm starting with noise, I want to wind up with noise. But the training data set and the modeling data can very easily get overwhelmed by the false signal. That's bad. I don't want that to happen. Now, can deep learning have this problem? Does it magically solve it? No. What happens, we make enormous dummy encodings and let things rip. This might work, this might not. I mean, the standard deep learning principle is embed all the things. But still, if I'm dealing with the zip code and I'm making 42,000 dummy variables, which is basically what embedding is, then I'm adding 42,000 variables of random noise. Some of that is going to look to training a whole lot like really important signal, flood possibly real signal, and also make overfitting very, very easy. So high category variables, not easy. Don't do target encoding. It just doesn't work. I'll be talking to you more. Bye.